Hi guys, nice to see everyone. Today we're going to be focusing on physics, and this session is going to be delivered by Preshayla, who is currently studying physics at Loughborough University, and it is her fourth year as a tutor at my tutor here. I think I'll give it over to you, Preshayla, now.
Oh, okay, so what we're going to cover today is all about forces and elasticity, and we're going to understand how an object changes shape and the forces required for it to change shape and the different ways that it can change shape. We're going to understand Hooke's law, which is the law that kind of governs elasticity. Then we're going to understand how we work out the potential energy stored in the spring, so the elastic potential energy. We're going to have loads of time for example questions today, and then obviously take your guys' questions. So not much content today. If you were there in the webinar yesterday, you know it was very content heavy, so we're going to have a little bit of a more chilled out webinar today with lots of your guys' questions. Okay, so first we're going to talk about change of shape. So there's three different ways that an object can change shape. It can change shape by bending, compressing, or stretching, which you can see here. We have bending, stretching, and compressing. So three different methods of changing shape. An object can change shape with either of those three or a mixture of them. So it could bend and compress. It could be a mixture of all three. So that's how an object changes shape. But to do any of those things, we need to have more than one force. So if we take a stationary object and we try to compress it, we need to have two forces, one on either side of the object compressing it. The same if we take a stationary object that we're trying to stretch. So we are taking our object and stretching it apart by using a force at either end. So there we go, we have another example of where we need to use more than one force for these shape changes to happen. And then for the final one, we have bending, and you can see that we need three forces for bending. So these green arrows represent where the force needs to be for these changes to happen. Okay, so for this one, we have a force either side. For this one, we have a force either side coming outwards. And for bending, we have three different forces. So you need to know that it requires more than one force for a stationary object to change shape. Okay, so for a stationary object to bend, compress, or stretch, we need to have more than one force in different locations. Okay, so we call it a change of shape, but the kind of more formal word for changing shape is deformation. So deformation is not kind of, it gets damaged, as you might kind of think from the word deformation. It's not damage, it's not going kind of, it's not going bad, it's not wearing down, it's just changing shape. Okay, so it's not a negative thing, it's just changing shape. So for deformation, we have two different types. We have elastic and we have inelastic. Now they're complete opposites of each other. Elastic deformation is the deformation can be reversed when we remove the force. So if we take an elastic band, for example, and we stretch it, it goes back to the same shape that it was in the beginning. That is called elastic deformation. If you have a hair tie, you stretch it out, it goes back to its original shape. That's elastic. However, there are some things which are inelastic, which means that the shape never actually goes back to what it originally was. So it's a permanent change in shape. We can never reverse what we've done to it. So for example, when we crush a drinks can, we deform it, we change its shape. But if we were to try and get it back into its original can form, it would never go back into the same original shape. So you squish the drinks can, you deform it, and then you try to reverse the deformation that you did, but you can't. It's never going to go back to its original shape. Okay, so that is called an inelastic deformation. It doesn't go back to its original shape. It's permanently deformed. It's never going to go back. So two types, elastic and inelastic, and they're very key to what we're about to cover next. Okay, so we have this law, this equation, which describes what happens when we put a force on an object to extend it. So the extension or compression of an elastic object is directly proportional to the force applied. That is Hooke's law. Okay, so we're not just talking about extension, although our equation does have extension in it. It's the same law for compression. So it's the same law if you're stretching an elastic band or compressing an elastic band, same Hooke's law. Okay, now notice that we have an elastic object. Hooke's law only applies if you have an elastic object. Okay, so an elastic object is, if you remember from the previous slide, it goes back to its original shape when we apply a force. So an elastic band, you stretch it, you apply a force, you let go, you remove the force, and it goes back to its original shape. So Hooke's law only applies for those types of objects, those elastic objects. With Hooke's law, in an exam, you're normally going to be talking about rubber bands or springs. They don't really kind of change it up. It's usually springs or elastic bands. So they're kind of some examples of elastic objects that you need to be confident and happy working with. So the extension is directly proportional to the force that we apply. But what does directly proportional mean? So directly proportional is when one thing changes, the other thing changes by the same amount. So if force was to double, extension would double. If force was to reduce by a factor of 3, extension would reduce by a factor of 3. So the same thing happens. Note that that's only applicable for timesing and dividing. So if a force adds 4, that doesn't necessarily mean that the extension adds 4. But if force is multiplied by 4, extension is also multiplied by 4. Okay, so that's what we mean by directly proportional to each other. Now, there's an extra bit to Hooke's law, which says that provided that the limit of proportionality is not exceeded. So the limit of proportionality is this limit that we have for the material that we're working with, where Hooke's law no longer applies. So it applies up to a certain point, but at that certain point, when we apply a force, it's no longer going to go back to its original shape. Okay, so the limit of proportionality is this upper limit that we have where Hooke's law no longer applies. Force is no longer directly proportional to extension. So the equation that we kind of have for Hooke's law is force equals spring constant times extension. So force is measured in newtons. We always measure force in newtons, no matter where the force is coming from or where it's going. Force is always in newtons. Then we have the spring constant. So this spring constant is a measure of how stiff the material is. So is the material easy to stretch apart, or is it really tough to stretch apart? How much force do we as humans, need to put onto this material to extend it. Okay, so if you have a really loose elastic bands are really quite easy to stretch apart, that's going to have a low spring constant. It's really easy to stretch apart. However, if we had a kind of stiff wire, for example, and we try to pull the wire, that's going to have a very, very high spring constant. It's very, very stiff. Okay, so a wire is very stiff and an elastic band is not. So an elastic band is going to have a much smaller spring constant than a wire, for example. Okay, so wires are very hard to pull apart. You're not really going to extend it by that much, even if you put a lot of force into it. And then the final part of our equation is extension, which is E. So extension, E, is measured in meters. So E is measured in meters, and E stands for extension. But extension can also be substituted for compression. So although the equation has E in it, which does stand for extension, it can also kind of be applied to things where we compress. Okay. So just to explain Hooke's law again, Hooke's law is when it's talking about how we extend an object using a certain force. And what it's saying is that if we apply a force, we extend it by a certain amount. If we then double the force that we apply, we double the extension. Okay, so we have, let's say we have an elastic band, we put a force on it and we stretch it a little bit. Then we double the force that we're stretching with, so we pull it out a bit more. That means that the extension is also doubled. So if we double the force, we double the extension. If we halve the force, we halve the extension. They're directly proportional to each other and they change in the same way. Hooke's law only applies to the extension and compression of an elastic object. Okay, so an elastic object is where if you stretch it, it will go back to its original shape. Okay, so we can show Hooke's law on a graph. Okay, so we're going to plot force on the y-axis, extension on the x-axis, so that K will be our gradient. You might have heard of y equals mx plus c, which is the equation of a line. So y equals mx fits our equation for Hooke's law, where we're going to plot force on the y-axis, extension on the x-axis, and spring constant will therefore be our gradient. There's no plus c in this. If you don't know the equation of a line as y equals mx plus c, don't worry. All you need to know is that we're going to be plotting force on the y-axis and extension on the x-axis, where force is measured in newtons and extension is measured in meters. Okay, so we're going to plot a force extension graph to investigate Hooke's law. And we can plot this graph for any material that we're investigating on. So this graph could be an example of an elastic band or a spring, for example, and we would draw a force extension graph. Now, this force extension graph has been plotted with two different sections. So you can see that there's a straight line section and then a curved section. So first of all, let's talk about the straight line section. the straight line section shows that force is directly proportional to extension. So if the graph is straight line, then force is directly proportional to extension and it obeys Hooke's law. Okay, so it's a linear extension that we have in this section of the graph. Everything's linear. If we change extension, we change force in the same way. So linear just means straight line. Now, elastic deformation happens in this straight line graph. Remember, elastic deformation is when you apply a force, it changes shape, you remove the force, it goes back to its original shape. So elastic deformation happens in this region of the graph, the straight line region of the graph. The object will return to its original length because it undergoes elastic deformation. Okay, so in this part of the graph only, up to this point here, we obey Hooke's law. We have extension proportional to force, force proportional to extension. And we can tell that because it's a straight line. And then for the other part of the graph, we have a curved part. So no longer a straight line, we now have a curved part. So non-linear extension, we don't have a line anymore. We have a curved part of the graph. We have inelastic deformation, which means it doesn't return to its original shape. So we apply a force, but now it's so permanently deformed, it's never going to go back to how it originally was. Okay, so we've stretched it out of shape. Here, in this curved part, we don't have Hooke's law applying anymore. We don't have force proportional to extension. We don't have a straight line. We have a curved line. Okay, so if we have a curved line, we do not obey Hooke's law. The object does not return to its original length if we go past this limit. So this limit really separates the linear extension part from the non-linear extension part. So the linear part is a straight line graph and the non-linear part is the curved part. And it's separated by this limit of proportionality. And it really is the limit of where it stops being proportional. So up to the limit of proportionality, we have force proportional to extension. After the limit of proportionality, they are not proportional to each other. We have a curved line. Okay, so you need to know these four kind of facts, these four ways to describe what is going on in each part of the graph. Another word for the limit of proportionality is the elastic limit. Okay, so now we're going to move on to talking about work and energy. So you might have heard of this key term work before. Now, work is a really important term in physics, and it basically means what is done when a force works to move an object. So work is done when a force works to move an object. So pushing, pulling, stretching, bending, compressing, all happen because of work. We, as humans, put work in to create a force to move an object. So stretching an elastic band, that's a human doing work to move the object. So the human is doing work, it's applying a force to move an object in some sort of way. So work is done when a force works to move an object. Okay, so work is not done if the force doesn't move an object, it doesn't change the object in any way. Work is only done when the force works to move an object. Okay, so work done. Now, a force that stretches or compresses a spring does work. The force works to move an object. It stretches the spring or it compresses the spring. And work is being done when we have that scenario. So when we stretch or compress a spring, we have work done. Now, if the spring is not inelastically deformed, so in other words, elastically deformed, if the spring does return to its original shape, if it is elastic, then work done equals the elastic potential energy. Okay, so the work that is done in compressing or stretching the spring equals the elastic potential energy. Now, elastic potential energy is what we have in springs, in bungee cords, in elastic bands. We have forms of elastic potential energy. And for an elastic spring, work done equals elastic potential energy. So what is elastic potential energy? How do we work it out? Well, elastic potential energy is kind of denoted with this big E, small e kind of symbol here. So the big E stands for energy, the little e down low stands for elastic. So this term represents elastic potential energy. Because it's an energy, we measure it in joules. And then we have the equation, which is elastic potential energy equals half times the spring constant times extension squared. So we need to do this bit first, extension squared first, and then times by the spring constant, and then times by half to get our elastic potential energy. It's the same spring constant that we had before in Hooke's law, and it's the same extension or compression that we had before in Hooke's law, but we're just using them in different ways. So spring constant, again, is still measured in newtons per meter, and extension or compression is still measured in meters. So our equation for elastic potential energy is half times spring constant times extension squared, where extension can be swapped out with compression. Okay, so this is another important equation that we need to know to work out elastic potential energy. It's one of those energy forms that you first do when you start the topic of energy. You have thermal energy, you have gravitational potential energy, you have light energy, sound energy, and now we have elastic potential energy. And this is the way that we work it out. Okay, so moving on, we're now going to talk about the required practical. So you may know that in GCSE, for a lot of the topics, you will have a required practical. And you may have done it in school, you may not have had the chance yet, but the required practical is an experiment that is quite simple that you can do in school, which helps us to understand the topic. So for the required practical for forces and elasticity, we're investigating the relationship between force and extension for a spring. So if we put more force on, what happens to the extension? Does it obey Hooke's law? Does it not? So the method that we need to use and the method that you need to memorize for the required practical is as follows. We're going to set up a clamp stand on our workbench using either a G-clamp or a large mass on the base. So this is an example of a G-clamp, this set up here. Or we can just put a mass on the base to keep it kind of balanced out. Now we're going to attach two clamps to the clamp stand, one at the top and one slightly further down. The spring is going to be attached to the top clamp and the ruler is going to be attached to the bottom clamp. We need to adjust the ruler so that it is completely vertical, completely parallel with the clamp stand, and with it 0 at the top of the spring. So you can see that the 0 level of the ruler and the top of the spring line up. So that's how we want to set it up. Now, for the measuring, well, first of all, we're going to start off with our slotted mass carrier. Okay, so a slotted mass carrier is this silver thing here. It kind of looks like a hook with a little plate on the bottom where you can put your masses on top. So first of all, we're going to measure the unstretched distance of the spring. So what is the original length of the spring? Okay, so it looks like it's roughly 5 here. So 5 centimetres for the original length of the spring. Then we're going to add on our slotted mass carrier. Now the mass carrier has a weight itself, which is 100 grams. So we're adding on a weight of 100 grams. Okay, so we're adding on a mass of 100 grams, which corresponds to a weight of 0.8 newtons. And if you don't remember the equation for this, no worries. The equation to get weight is mass times G. And G is just 9.8. So we need to know how to convert mass to weight by timesing by G. Remember that mass is always in kilograms, so we also need to know how to convert a mass in grams to a mass in kilograms. So we have our first weight going onto the spring, which is 100 grams. The spring is obviously going to extend a bit, and we're going to measure the length that the spring goes to. So it's going to extend, and we're going to measure the new length of the spring. Then we're going to take them away from each other to find out how far the spring has stretched. How far down has the spring extended? We're going to keep doing this, adding masses, 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 until we get to 1,000 grams. So we're going to add on 10 masses. And each time, record the new length of the spring. So we're going to get a results table that looks a bit like this. Force, length, and extension. You can choose to do the measurements in whatever you want, millimeters, centimeters, or meters. Millimeters tends to be what we recommend. However, you can do it in centimeters, as long as you do then convert it into meters to work with in either the Hooke's law equation or the elastic potential energy equation. So force is measured in newtons, and remember, we don't really care about the mass, we care about the force. So we need to convert the mass into the force by timesing it by G first. So we're going to get forces, which start at 0. So before we add anything to the spring, what is its length? And there'll be no extension because we haven't added a mass. Then we add a mass, which provides a force of 0.98 newtons. We then get the spring extending, in this case, by 30 millimeters. So our extension is 30 millimeters. We then add another mass, we calculate the force, and we find the new length and how much it's extended by. So you can see from here to here, we've extended by 61 millimeters. So it's important to measure the extension from its original length and not from the length before. So you can see that 22 to 52 is 30, and 52 to 83, and 22 to 83 is 61. So we're measuring the extension from its unstretched length, its original length, before we started adding any masses. And we can plot a force extension graph. Once we start getting a results table, and we're going to be doing this up to 10 masses, up to 1,000 grams, we can plot our points on a graph where we plot force on the y and extension on the y and force on the x. This is different to what we had before. So before we had force on the y and extension on the x. It doesn't really matter what way around you do it, but note that the gradient will be different. So we always say to do force on the y-axis and extension on the x, because then the gradient will be k. But if you do extension on the y and force on the x, the gradient will be 1 over k. So it's just kind of another step and extra work that you don't need to do. So always plot extension on the x and force on the y. Okay, so that is how we conduct our required practical experiment. You need to know the method. You need to know what kind of results table would you produce, what would you put in it, and what would the graph look like when you did plot it. Okay. So that is the end of the content. I'm going to go through some of your guys' questions now, and do put on any questions that you have in the chat, and I'll try to answer them. Okay, so somebody asked what are the units for the constant and extension. So for the units for the spring constant, it's newtons per meter, and for extension, we're just measuring a distance of how far the spring stretches, so it's in meters. So someone asked, so when the spring is stretched to a deformed shape that they can't return to normal, then is it work done equals elastic potential energy? So if our spring cannot return to its original shape, then this does not apply. Work done does not equal elastic potential energy. However, if we stretch the spring and it does return to its original shape, then work done does equal elastic potential energy. So our object needs to be elastic. It needs to have elastic deformation for this rule to apply. Do different springs have different limits of proportionality? Yes, that's a really good question. So yes, different springs have different limits of proportionality. It depends on the material that they're made out of. Would plotting a graph get you extra marks? It really depends. They're not going to, they kind of need to give you the graph paper and the area for you to be able to draw a graph. So they'll therefore have to put it into a question. However, if it was kind of a question of describe a method that you would do to investigate how force changes with how extension changes with force, then you might want to say, I would plot a graph of this against this so that the gradient would be this, and that would get you extra marks. Yes, that would get you, that would be a really great thing to say, and it would definitely get you some marks. So always allude to the graph in a required practical question, as it's really what helps us to kind of work out what we were investigating. So for the required practical, we're trying to investigate the spring constant, which we can't do without a graph. Okay, I think that's all the questions. Someone said go back to slide 8. There you go. The slides will all be uploaded to YouTube, so don't worry about that if you haven't got it down.
I've got some questions here as well, Preshayla.
Go ahead.
I've got one from that kid, and it goes as this. So when the spring is stretched to a deformed shape that they can't return to normal, then is it work done equals elastic potential energy? Or does work done equals elastic potential energy apply to just the spring being changed in shape, and how much force is needed to change the shape?
Okay, so work done equaling to elastic potential energy only applies to elastic objects, so objects that are elastically deformed. So if an object can be stretched and when we let go it returns to its original shape, for example an elastic band, then work done does equal elastic potential energy. However, if we're talking about something that is inelastically deformed and doesn't return to its original shape, then this equation does no longer apply. Now, in an exam, they could either ask you to find out the work done or the elastic potential energy. So you need to know that these two are equal to each other because we don't have a equation that has work done in it. So you need to know that work done equals elastic potential energy if it's an elastically deformed object.
Perfect, thank you. I think a lot of people are asking for the practical diagram, to see the practical diagram again.
So it's this diagram here. We have a clamp stand, we have two clamps, we have a ruler so that we can measure extension, we have our spring, and then we have a mass carrier so that we can keep adding masses on.
Perfect, thank you. Guys, continue to send in your questions, preferably on the chat. Preshayla, is there anything else that we can cover question-wise?
Yeah, so we'll go through some example questions now to give you guys a chance to put some more of your questions on the chat, and then at the end I'll do another kind of question session.
Amazing.
Okay, so we have our quickfire questions. So if you've ever been in a webinar before, we always do our quickfire questions. So they're just multiple choice questions. Put your answers in the chat or just think about it to yourselves. So the questions are: how might the shape of an object change if forces act away from each other in a straight line? So forces opposing each other. And then for the other one, how might the shape of an object change if forces act towards each other in a straight line? So we've got forces acting away, forces acting towards each other. What would happen? Okay, so for the first one, Leslie putting the correct answer in the chat, which is it might extend. So if you think about two forces pulling away from each other, if you just kind of even do it with your hands, or if you have a elastic band or a hair tie, you can really experiment with it practically, which is a really great thing to do with forces and elasticity. If you pull the two forces away from each other, it will extend. If the forces act towards each other, it will compress. And someone even said that it might also bend, which is really great. Although this is a multiple choice question, it could also bend. So if you ever think about like bending a ruler, so if we bend a ruler, compress a ruler at both ends, right? I'm pressing it at both ends, but as soon as I stop putting a certain force, it bends, right? So I'm compressing it, I'm putting my two forces towards each other, but it starts to bend. Okay, so if the object, if the forces act towards each other, so I'm pushing in this way with this hand and in this way with this hand, so my forces are acting towards each other and they do compress the ruler to a certain extent, but actually it bends as well. Okay, so the correct answer for this generally would be compression. So for something that can be compressed, like clay or some sort of food type, we can compress. But some certain objects like solids might not be able to be compressed and might bend under the forces instead. So compression generally, but also bending can happen. Okay, which word describes an object that will return to its original shape when forces are removed? Great, loads of you are putting elastic in, that's the correct answer. And what about number 4? What word describes an object which will not return to its original shape when forces are removed? So it does not return to its original shape. Inelastic, brilliant. So elastic when it does return to its original shape, inelastic when it doesn't. Okay, what is another name for the limit of proportionality? So it was on the graph. Which word describes the limit of proportionality? Cool, some of you are saying the elastic limit, that is correct. It's where the object stops behaving elastically. If it passes the limit of proportionality, when we apply a force, it will no longer go back to its original shape. So before the limit of proportionality, we have elastic behavior. If we put a force on, it will always go back to its original shape. But as soon as we pass that limit of proportionality, when we apply a force, it doesn't go back to its original shape. So another word for it would be elastic limit, because it's the point at which the object stops behaving elastically and starts behaving inelastically. For the second one, what is the unit for the spring constant? That is newtons per meter. Newtons per meter. So if we have F equals KE, and we know that F is measured in newtons, K is measured in newtons per meter, and E is measured in meters. Well, if we were to rearrange this equation for K, we'd get K equals F over E. So we know that F is measured in newtons, E is measured in meters. We're doing newtons divided by meters, so newtons per meter is what the spring constant is measured in. So if you ever do forget, just rearrange the equation for K and think about what the units of force are, what the units of extension are, which is newtons per meter. So we know that K, the spring constant, is newtons per meter. Okay, what is the name for energy stored by a stretched spring? What's the name for energy stored by a stretched spring? Great, it's elastic potential energy. Anything to do with springs, bungee cords, hair bands, rubber bands, elastic bands is going to be storing elastic potential energy when it's stretched. So if it's just in its original form and it's just kind of sat there, then it doesn't have elastic potential energy. It's only when we stretch it does it store elastic potential energy. Which equation then gives the energy stored by a stretched spring? Is it E equals KE, E equals half K squared E, or E equals half KE squared? Okay, great. It's E equals half KE squared. So remember that we need to square E first and then times by K and by half. Okay, questions 9 and 10. This is going to require you to do some maths now. A spring extends elastically by 10 centimeters when a force of 20 newtons is applied to it. What force would be needed to extend the spring by 5 centimeters? So this is a multi-step question, and it can be quite tricky because it does have 2 different steps in it. So the first thing that we need to do is work out the spring constant. We've been given a force and we've been given an extension, so we can work out the spring constant using our equation KE. Now, to work out the spring constant, we can rearrange the equation to get K equals F divided by E. Now, remember that force is measured in newtons, but extension is measured in meters. So we need to get 10 centimeters in meters. So 10 centimeters in meters is divided by 100, so we get 0.1 meters. So our extension in meters is 0.1. So when we do 20 divided by 0.1, we get 200. So we know that the spring constant of this specific spring is 200 newtons per meter. Now we want to work out what force would be needed to extend the spring by 5 centimeters. So we need to work out a force, which means we do spring constant times extension. We now have a value for spring constant, which is 200. And we want to work out the force that would be needed to extend the spring by 5 centimeters. So again, we need to convert to meters. So 5 centimeters in meters is 0.05. So our extension is 0.05. So the force required to stretch the spring by 5 centimeters is going to be 10 newtons. Well done if you got that. It's quite a tricky question with quite a lot of steps, so don't worry if you didn't get it first time, but hopefully it makes a little bit more sense now. The steps that we need to go through are, first of all, to find the spring constant using the information that we've been given of how the extension changes when we have a force, and then what force would be needed to extend the spring by 5 centimeters. Now, there is a different way to do this. We need to remember the fact that force is proportional to extension, which means if we halve the force, we halve the extension. If we double the force, we double the extension. If we halve the extension, we halve the force. If we double the extension, we double the force. Okay, so the same thing happens to force and extension. Now, we know that we have an extension of 10 and a force of 20. The question then asks, what would happen if we halve the extension? You can see that we halve the extension from 10 to 5. Well, we know that if we halve the extension, we halve the force because they're proportional to each other. So if we halve the extension from 10 to 5, we halve the force from 20 to 10. So you can see that there are 2 ways to do this question. It's absolutely fine for you to do it the mathematical way, the slightly longer way, or you can kind of do it in your head thinking that if we halve the extension, we halve the force. Whatever we do to the force, we do to the extension. Okay, so either way is absolutely fine for this question. Now, the second one says that a spring extends elastically by 0.1 meters when a force of 2 newtons is applied. What is the value of its spring constant? again, we're going to be using our F equals KE. And rearranging for K, so K is F over E. And if we do 2 divided by 0.1, we get 20. So well done if you said 20 newtons per meter. Okay, so now we're going to be doing some questions about potential energy. If you don't remember the equation, it's E. The energy is half KE squared. So for our first question, a spring which has a spring constant K is 7.5 newtons per meter has been stretched 0.4 meters. Okay, so our spring constant is 7.5 and our extension is 0.4. What is the potential energy? So we've been given K and we've been given E, so we need to put it into our equation for potential energy. So E equals half times K, which is 7.5, times E squared. So E would be 0.4, and we need to remember to square it. So 0.4 squared. So have a go at putting that into your calculators. We've done half times the spring constant times the extension squared. What would that give you? Give you a few seconds to put your answers in the chat. So remember to square 0.4 first, then times by 7.5, then times by 0.5. Okay, so we get 0.6. So the potential energy that we have stored in the spring is 0.6. And remember that that is measured in joules because energy is always measured in joules. And then for the second question, we have been given the spring constant and we've been given the energy. We need to work out the distance. So this one's a little bit more complicated. It requires us rearranging for E. So we've been given EE. Now we can times both sides of our equation by 2 to get 2E is KE squared. Okay, so I've just times both sides by 2. Then I'm going to divide both sides by K so that I get E squared. Okay, so that's how to rearrange the equation. And then we can square root it at the end to get extension. So for this question, we're talking about compression. So remember that the Hooke's law and the elastic potential energy equation apply to either extension or compression. Now we can substitute our values into our equation. So we have E squared equals 2 times energy over spring constant. So 2 times energy is 392 divided by spring constant 800 equals 0.49. Okay, so that's E squared. And then we need to square root both sides. So E squared equals 0.49. To get E by itself, we need to square root both sides. So square rooting E squared gives us E. Square rooting 0.49 gives us 0.7. And that's our final answer. So the extension, the compression in this case is 0.7 meters. So we need to be really comfortable on how we can rearrange this equation to get anything we want. So you guys need to practice rearranging this equation for K, for E, and kind of the steps involved in doing that, and be comfortable with square rooting. Obviously we'll have a calculator, but you need to know that if you're left with E squared, you need to square root the final answer to get the actual extension of compression. Okay, so going to stop there and take some more of your guys' questions. So put them on the Q&A, put them on the chat. Does anyone want me to kind of go back to the slide and explain it again? Okay, it doesn't look like anyone's got any more questions, so we can do another example question. Okay, so there's two questions actually just come in. So would compression lead to bending? Yes, compression can lead to bending. For example, it only takes a little bit of compression of a ruler, a bendy ruler, for me to bend it. So I'm compressing, and then see, it starts to bend. So yes, compression can lead to bending.
I've also got some questions here. So someone wants to know, if they're doing the higher tier exam for science, do they have to learn all the equations, or are there specific ones only for higher?
No, so for higher tier, you don't need to know all of the equations. You will be given an equation sheet. If you want to look at the equation sheet, just type in GCSE Physics, your exam board equation sheet, and it will tell you all the equations that you need to know. Any equations that aren't on there are the ones that you obviously need to learn. Otherwise, go on to the syllabus for your exam board, and it will tell you this equation needs to be known, this equation will be given. But yeah, there aren't specific ones kind of that you need to that are different for foundation and higher.
Okay. Super helpful. Someone also wants a quick summary of what the spring constant is.
Okay, so the spring constant is really this measure of how stiff an object is. So how easily can it be stretched or compressed? So for an elastic band, we know that it can be really, really easily stretched, right? We don't need to put much effort in to stretch it or to compress it. So that would have a low spring constant. It's not very stiff. It's really easy to stretch. So a low spring constant, a low measure of stiffness. However, on the opposite end of the scale, we have, for example, a wire, right? It takes a lot of effort to stretch it. It's very, very stiff. And so it has a very high spring constant, a very high measure of stiffness. So it's really this measure just of how stiff a spring specifically, or any object, is.
Great, thanks. Conscious of the fact we've only got 1 minute left, is there anything you want to share? I see that someone wants some useful websites. Is there any recommendations you have?
Yeah, so Physics and Maths Tutor has all the stuff that you need. It's all divided by topic, and it's where I get my questions from. I think it's a really great website. So Physics and Maths Tutor for past paper questions. There are also notes on there if you would like them. Save My Exams is also a good website, but do bear in mind that it doesn't have the answers. Usually you have to pay to get the answers, so it can be useful for questions, but do bear in mind you won't be able to check your answers. So I would definitely recommend physics and maths tutor. Otherwise, bite size is good for content, but not so good for questions.
Perfect. Thank you so much for this session, Preshayla. It's been very useful. We have now run out of time. Thank you everyone for joining us. Have a lovely evening and keep safe. Bye.
Thank you. Bye.